All right. Hello, everyone. How are we doing? Okay, this is the beginning of a series where I'm going to be building a entity component system from scratch and recording myself as doing so. So to give you a little bit of context, I'm working on a game engine in C++, and this is a part that I thought was pretty interesting to share more in detail. So I have built a couple of entity component systems in the past, and this time I want to do it right. So first, a little introduction as to what is an entity component system, also abbreviated as ECS. Maybe I'm going to use this from now on because entity component system is a bit of a mouthful. I'm not going to go into too much detail on what it is and why it is the way it is. I think there's a lot of good content out there on what it is. So what I will do is that I will try to give a very brief introduction and focus on the constraints that we want to have in mind when building this system to make it very optimized. So let me switch the view here to my tablet. All right. So entity component system, what is it? In a game, you are manipulating, you're creating, what is a game, a video game? It's basically a simulation where you have a lot of objects or entities, or you can call them whatever you want, that interact with each other. So you need to think of abstractions for all of this, unless you are very much against the object-oriented paradigm and you only use functions. You want to use some sort of an object to represent, and by object in this case I mean a code object, to represent concepts in your games. For example, you have a player, right? So let me draw a little player. This player has a sword and is fighting some kind of a monster. Let me try to draw. Okay, this is a beautiful monster. So what are these in your code going to be? Usually you're going to have objects to represent all of this. So you're going to have maybe a player object, a sword object. Let me write class in front. And maybe a monster. So the most naive way you could think of doing this is create one class for each one of these, and this class has a lot of attributes that represent, I don't know, the player position, the player health, etc. But then you're going to realize that you're going to be duplicating all of this. The monster also has a position. It also has health. It probably has different methods. But the next step is probably thinking about using inheritance for this. Okay, so you could say, okay, the player and the monster, they both have a position. They both have a health. They probably both inherit from a class that we're going to call. What are we going to call this? We're going to call this a I don't know, a live being. I don't have any imagination when I'm on camera. I don't know how to name stuff. It's going to be a being. My God, I don't have any imagination. Okay, so you have this superclass being that has a position and a health, and then you can just say that your player is a being and your monster is a being. So you can get somewhere like this for like a very simple game, but as soon as things start being complicated, you're going to run into problems because inheritance defines mostly a tree of things. So you have your being, you have your monster, and you have your player here. My handwriting is great. And I'm seeing that the video of myself is on top of the canvas, but that's okay. What happens when you have, for example, a sword could probably have some health. If you want your player to have a sword that can break after you use it for a while, you would maybe just want it to have some kind of health. How do you handle this? Because your sword is not a being, it's not a monster, it's not a player. You're gonna have to tweak your hierarchy in some kind of sordid ways there. So what you end up doing instead is using entity component system. This comes from the paradigm of composition over inheritance. Essentially, what you do is that you have a very shallow hierarchy. Maybe you just have an entity as a class, and every single object in your game, the player, the sword, the monster, they are all an entity. But what they have is they have access to a list of components. And these components, they encode some sort of behavior. So maybe you're going to have, so this was the wrong paradigm to take. Well, I'm going to make this claim. What we're going to do is we're going to have a class entity. And this class has some kind of a data structure, maybe, of components. And these components, they're going to be things like position components. Okay, this tells you where in the world is your object. They're going to have like a health component for everything that is alive and can die in your game. They're going to have maybe an AI component. This way, you're going to use this to animate all of the monsters in your game. Okay, and this is way more flexible because this means that, you don't have this problem of hierarchy anymore. It's very flat. Like you just give to each entity the components it needs, and you're sorted. You can also add components at runtime or remove them. So, for example, say you've got a camera in your game, right? The camera is an entity, and it has a camera component. It's probably going to be attached to your player. But say that you want to take control of an enemy, then what you could do is just remove the AI component from the enemy, attach a camera component to it. You can attach like a player controller component. It's going to be something like this. Okay, so that's the rough idea. Now, let's talk about constraints. What do we need from our entity component system to be good? And by the way, I've not talked about the system part of entity component system. Very briefly, the system so you're going to usually define your components as pretty much data structures with almost no logic, and the systems is where the logic is encoded. For example, if you have an AI component, that's a good example. Your AI component is going to just contain some data about the entity that holds it. So maybe there's like an aggression level. All right. Aggression level equal 4. This is a very aggressive monster, this one. And what else could it have? Could have a I'll just keep it at this for now. What you're going to have is that you could think of like attaching a lot of methods to these components, saying, is attacking. This could be a method that returns a boolean, whether this specific AI wants to attack you or not. And you could have like tons of methods like this. It's not how usually we want to do things. Instead, we want to have something like only a singleton or like a static class called an AI system. And this AI system, it's going to loop through all of the AI components in your game, and it's going to use the data that they contain and do the update. Your game is basically a big loop. right? And throughout this loop, you're going to update all of your entities. That's the idea. So, for example, there's a player. Every frame, you look at the player's position and you update it according to the controls, the inputs that you have received. During this loop, you're going to update your systems. Instead of updating your entity or your component, you just update your system. So maybe you have a player position system or whatever. You update it, and during this update, it's going to loop through all of your entities, or rather, all of your components, or all of your position components, and it's going to update them. So now, knowing this, there is some very important thing to have in mind. If you want to have a lot of entities in your game, and I'm thinking maybe you can push it to like 100,000 or 1 million entities, what is the problem you're going to have? You want to basically be able to loop through a lot of components. All right. How do you do this fast? Let's talk about how a computer works. So in a computer, you have a CPU. Let's represent it like this. This is my CPU. Okay. You have the RAM, which is your memory. You have the hard drive, let's say, somewhere. Well, these days it's often a solid state drive. But anyway, what happens is that the RAM is pretty big. It can be, I don't know, these days I don't know what the standard is, 8, 16 gigabytes, maybe more. When you start your program, a lot of memory is allocated for it in the RAM, and that's all your program needs. Normally, it should never use the hard drive memory because access to this memory is super slow. So you have different types of memory in your computer. You've got the hard drive, which is extremely slow to access. You've got the RAM, which is relatively fast, but you have something much faster. You have, I don't remember what they are called in English, probably registers close to the CPU. You have a bunch of registers. I think you have 3 levels. And by the way, I am not an expert in all of these, so yeah, I don't know. Well, I just want to share what I know. But if I'm saying anything that is completely rubbish, please let me know. One aim of this series is also for me to learn by getting any sort of feedback. I assume I'm not going to get much feedback at the beginning because I'm probably not going to get any viewer. But just in case you are watching this video and you realize that I say something nonsensical, please let me know. Write in the comments. Okay, so where was I? So you've got a CPU. You've got some memories called the registers, which are super close, even physically speaking, to the CPU. They are actually in the CPU, I think. Yeah, they are part of it. And the RAM is far. So when you want to pull data from the RAM, it takes time. It takes latency, right? You can have a high throughput, which means you can take a lot of data at once. Oh my God, this arrow is. Oh my God. Anyway, this is an arrow. And this is a fat arrow to show that you can take a lot of data. But there is some time here. So there's a delay that happens here. From the registers to the CPU, this delay is a lot less, probably 100 times faster, something like this. So anyway, where I want to get with all of this is that if you want to iterate through 1 million things, what happens with the computer? Naively, you'd think, well, these things are in the RAM, right? This is data that lives in your RAM, and I'm talking about the components at the moment. They live in your RAM. They're going to be accessed one at a time, right, throughout your loop. So you'd be thinking, okay, the CPU gets one of these elements from the RAM, does an operation on it, and then goes to the next one. But it actually does something a bit different because there is a delay, but there is a large throughput from the RAM to the CPU. What the CPU does is that it doesn't just take one bit of information. It takes a whole lot It takes basically, well, let's look at the memory inside the RAM. Okay, let's say that this is your memory. It's basically a bunch of consecutive bytes. And the information you want to access is here. This is your transform component. Let's say this is sorry, I'm talking about transforms, getting ahead. This is your position. Let's just call it position. Okay, this is a player. This is the position of the player. The next one is going to be the position of a monster, etc. We want to access all of these one at a time and do some operations on them. What happens is that it's not just one of these that gets pulled from the RAM into the CPU. When the CPU is told to access one, it's going to actually take a whole lot of data around it, and it's going to put it in one of its registers, right? So then suddenly you have your position here, but you have all of the data that is around it in your memory that is in a place where it can be accessed very quickly by the CPU with very low latency. What this means is that you should put all of your components, you should store them consecutively in your memory. You should be basically aware of this, because if instead of having them tightly packed like this, so here I have position 1, position 2, instead of this, if they were all over the place, and this is what you would get if you were, for example, allocating every component on the heap and just storing pointers in an array, they could be anywhere on your RAM. What is going to happen is that instead of accessing, instead of like copying a whole lot of data at once from the RAM to the CPU, what's going to happen is that the CPU is going to, well, it's going to still copy a lot of data, but it's only going to have one of your components accessible. And when it needs to go to the next one, it's going to have to go back to the RAM and copy a whole lot of data again. And this copying of data is the operation that has a large delay and that we want to avoid. So yeah, long story short, you need to store your components in a tightly packed array so that they can be accessed fast. So that's one constraint I want to have for this system. The next constraint maybe is going to be a nice API. That's always good. And for the API, I just took inspiration from something called ENTT, which is an entity component system that is open source, I believe. It's free. It's really good, I've been told. I've not used it myself. And any sane person would just use it instead of writing their own. But I really like this, so there's no good reason for me to do this, but I'm going to write my own entity component system. Actually, I've already done it. I've written a fairly efficient one, but I want to optimize it a little bit more, so I'm going to redo it from scratch in front of the camera. And yeah, I guess that's it for this video. Thanks a lot for watching, and in the next video we're going to actually start coding, and yeah, I'm going to try to show you how I go about writing a very, very lightweight, because I'm just myself, and I'm going to be trying to write something very minimalistic that does what I need, and very performant entity component system. All right, see you everyone.